Welcome to Chemistry at Honeyniga High School. I'm Brian Brown, and today we'll be looking at our first set of notes over Chapter 15, which deals with states of matter, our solids, liquids, and gases, and understanding them better. Now, first, we're going to start off with gases. Now, when we talk about solids, liquids, and gases at a particle level and trying to understand and explain their behavior, we use what's known as kinetic theory. Now, kinetic means movement, so kinetic theory explains the behaviors of particles in terms of their motions. So kinetic theory as it applies to gases, well, there's four fundamental things that we're going to look at. One, individual gas particles have a negligible volume, which means the volume of a gas isn't measured by measuring the volume of the particles, it's by measuring the volume of the container. And that's because each individual gas particle is incredibly small and independent of the others. And remember, negligible doesn't mean no volume, it means so small we ignore it. The second thing we believe to be true and used to explain gas behavior is that they move in rapid, constant, straight line motion. So they're moving very rapid compared to the solid and liquid states, and they're in constant, rapid, straight line motion. Third thing, they collide elastically. Now, elastic is a term you may have heard of, but it's usually when students don't really get what it means. Well, when you collide elastically, that means in the collision, there's no net loss in kinetic energy. Kinetic energy is the energy of motion. And when particles collide into each other, kinetic energy can be transferred from one to the other. So a slower moving particle may be sped up and a fast moving particle may slow down, but overall they didn't lose any kinetic energy, which should make sense. Otherwise, as gases collided with each other, they'd get slower and slower and slower, which means they get colder and colder and colder until everything got really, really cold. And your gases would then condense back into liquids, and your liquids would then freeze into solids, and that just doesn't happen in everyday life. So there is no net loss in kinetic energy when particles of gas collide. And then finally, the gas particles are very far apart and have no attractive or repulsive forces. Now, really a better word here would be negligible attractive and repulsive forces, because what happens is the particles are moving rapidly, speed kills attractive forces, and they're far apart. Distance kills attractive forces. So between those two factors, the attractive forces really become negligible when we're looking at gas behaviors. So when we talk about and explain gases, those are the fundamental behaviors with which we look. And you can see here at a particle level, you've got gases very far apart, moving in rapid, constant, straight line motion. And that's how we would expect gases to be moving at the particle level. Now, remember, kinetic theory is the energy of motion. Well, what is kinetic energy? Well, it's the equation 1/2 mv squared, where m is the mass and v is the velocity. Now, we're not actually going to do calculations, but in order to understand kinetic energy changes, you need to understand the particles that, or the variables that make it up. Now, in the case of mass, normally we're looking at an object that we're heating up or cooling down, so its mass doesn't change. So in many situations that we're looking at, the mass is going to be constant, but that doesn't mean the velocity is constant. As we dump energy into particles, the average kinetic energy increases. Well, since our mass isn't increasing, that must mean our velocity is increasing. And when you double mass, you double kinetic energy. But when you double velocity, 2 squared is a factor of 4. So it has a much greater effect overall on changes. But if we were looking at two things, two different types of particles that were at the same average kinetic energy, it would be true since they weigh differently, they aren't moving at the same speeds. And that's an idea we're going to come back to later. Now, temperature is a measure of average kinetic energy. So when we measure the temperature of a substance, that gives us knowledge about what the average kinetic energy of the particles are inside that substance. And remember, molecules within a substance, while they're at a constant average, that doesn't mean they're all moving at the same speed. It just means they have a constant average speed. You have some high speed and some low speed, and many molecules moving around what the average speed is, but they're not all moving at the same speed. And that's a common misconception for students. So they have a constant average speed. Just like if the amount of money in my room is constant, that doesn't mean everybody has the same amount of money. Now, a good diagram to look at this, and we're going to use this in a couple of different chapters, so you're going to see this idea a few times. What we have here is a graph where we're looking at the percent of molecules on the y-axis versus the kinetic energy as increasing across the x-axis. So they're color-coded. That helps you visualize the idea here. When we have a lower temperature situation, like in iced tea, versus a higher temperature situation, like in hot tea, a common confusion or misconception by students is they see that blue one has a really high hill. That must mean it has a lot of energy. Well, remember, the average is really what we're looking at here. And for the blue situation, the average is going to be right around that spot because you'll notice there's a few more on the higher average kinetic energy. So that's going to shift our average a little bit past the hump. Well, that's where the average kinetic energy of those particles is. Now look at the other situation. Its average is going to be right around there. So even though the hump is smaller, it's actually at a higher average kinetic energy. That's because the y-axis isn't kinetic energy. It's on the x-axis. And here is where our averages are. So obviously in hot tea, you end up with a higher average kinetic energy. So the higher the temperature is, the more that hill gets spread out and pushed down and moved over to the right. The area under the curve in each case is actually the same. That would represent 100% of the particles. So that can't change. So as we add higher energy particles, the hill gets lower and lower and lower. So if I give you a graph similar to this in the test and I ask you what's the highest temperature, you're going to pick the one with the lowest hill. It's going to have an average farthest to the right. If that's what the lowest temperature is, you're going to pick the highest hill. It'll have an average farthest to the left, or lowest in kinetic energy. So in this case, color-coded, red would be the correct answer. Now, the higher the temperature, the faster moving on average our particles are. And the colder it gets, the slower moving they are. Well, the only temperature scale that really is directly tied to the speed of motion would be the Kelvin scale, because at 0 Celsius and 0 Fahrenheit, we can still get colder. We can get below 0. But at 0 Kelvin, all molecular motion will have stopped. And that's a theoretical impossibility to reach. We can get very close to 0 Kelvin, but we can't actually make a particle freeze. So one of the things you should know for the test is all particles are in constant motion. Some are moving faster than others, but they're all in constant motion. Now, as we start to get into understanding gas behavior a little bit, one of the important variables we're going to look at is really something that's very important for wind. Wind can be an incredibly, incredibly strong force. And you've all felt wind hit your face. So there must be something there. You can't see anything, so hopefully it's obvious. It's those air molecules that are moving at you and colliding with you. And when those collisions increase in force, that's what we're talking about by wind. So what we're really looking at here is pressure, the simultaneous collisions of billions of molecules with an object. In the case of wind in your face, that object is you that those particles are colliding with. So pressure is really dealing with collisions. So whenever you think of the term pressure, you need to visualize collisions. Anything that would make more collisions or higher force collisions or concentrate a number of collisions in a very small area would lead to higher pressures. And that's because pressure actually equals mathematically the force divided by area. Like kinetic energy, this isn't a calculation I want you to do. It's a conceptual understanding that I want you to have. If we do something to increase the force, we're going to increase the pressure. But since area is on the bottom, when we increase the area over which our force is being exerted, that's actually going to decrease pressure. So remember that force that we're talking about is created by the collisions of the gaseous particles. The more collisions we've got, then the higher the force, the higher the pressure. And also the harder the collisions. Force is actually the mass times acceleration. So when we get more collisions and harder collisions, both of those are going to end up increasing the force and therefore increasing the pressure. But on the flip side, if we play with area, we can also change pressure, but in a very different way. Thumbtacks and snowshoes take advantage of this. So in the case of a snowshoe, you're walking on the top surface of snow. It doesn't take a very high pressure to break through and fall down into the snow, and then it's very hard to walk across it. So if you take all of the force that your body is exerting as it pushes down, which is the area of the bottom of your feet, and you spread it over a much larger area, that's going to decrease the pressure that you exert against the snow. And if you lower the pressure enough so that you don't break through the snowpack, then you're literally going to walk across the top of the snow. So you'll be able to walk through snow much more easily. Another example of this would be if you're walking out on ice and you hear it start to crack. Now, most people's first inclination is to, get off the ice as quickly as possible. Well, when you go to do that, you end up slamming your foot down even harder, creating even greater pressure. And typically, you're going to be running and hitting one foot and then another foot, and then that's actually going to increase your pressure too when you have a much smaller area. What you want to do to be safe is increase your area as much as possible. So immediately lay down on the ice and then maintaining as much body contact with the ice as possible, which gives you a huge surface area, low pressure, swim off the ice, and you're much more likely to be safe. On the flip side, thumbtacks, we want them to exert a great deal of pressure so we can push right into an object. So the object is holding onto itself and held together by strong forces. But if we push hard enough, we can break through those forces. And that's why we have a very fat end. So the same force is giving us over a large area a low pressure, but on the other end, a very sharp pointed end. So once again, the same force concentrated into a very tiny area means a very high pressure. So when you're pushing a thumbtack against the wall, the pressure that the thumbtack is pushing against your thumb is not the same pressure that it's pushing against the wall. It's the same force, but not the same pressure because of the area difference between the two. And also is a problem potentially with high-heeled shoes. For any female students ever worn high-heeled shoes, when you walk out off the hard surface, you push right into the dirt very readily. Or if you're walking across a gym floor, you exert such a high pressure, you can actually dent the gym floor if you're not careful. So pressure, collisions of particles, and its force per area. Now, if we took away all of the particles like in a vacuum, we've got no collisions. That means no pressure. Atmospheric pressure, on the other hand, we're surrounded by a sea of air, and those particles are constantly hitting us. And the other thing that people forget about is it's not just the particles around you, but it's also the particles above you stacked on top. Picture one book sitting on your head. That's going to exert a pressure that you can feel. But if you put 2, 3, 4, and 5, none of those books are touching your head. But the pressure that you're feeling on top of your head is going to be significantly greater. So we're walking around a sea of air with air above us. And we basically have a column of air on top of our head that's pushing down. We just don't happen to see the column of air. So consequently, because we live at the bottom of this big ocean of air, when you walk up a mountain, the column of air above your head is getting less and less and less. So atmospheric pressure is going to decrease because of the depth of air difference as you move up into the atmosphere. Now, what do we measure pressure in? Well, there's a variety of different units we're going to see. And one of the things you'll end up practicing in this chapter is some simple conversions. So dimensional analysis we're going to use again here. Now, our SI unit of pressure, probably should know that for the test, is the Pascal. So Pascal actually stands for a number of different units combined, but the simplest way to look at it rather than all the kilograms and meters and seconds is to just combine into one unit that we call a Pascal. So that's our SI unit. So you're going to see pascals and kilopascals from time to time. Another type of pressure we're going to see is atmospheric pressure, and that's typical sea level pressure. And this is a really common, easy one to understand. So if someone says, well, the pressure is 1.2 atmospheres, you know that's a little bit above normal atmospheric pressure. 2 atmospheres of pressure. Well, that would be double atmospheric pressure. So atmospheres is another common unit. And then the last one we see, and this is really because of barometer and manometers, ways in which we have of measuring different types of pressure, is millimeters of mercury. Well, how is a length a pressure? Well, remember, if you have a length of a very specific diameter of mercury, the taller that column of mercury is, the more pressure it's going to exert downward. So millimeters of mercury, a length of mercury, can also be a form of pressure, but it's really a very specific diameter column of mercury we're talking about. And barometers are commonly columns of mercury, so we measure them in millimeters of mercury. Now, if you look at how these compare, 760 millimeters of mercury is equivalent to 1 atmosphere, which is equivalent to 101.3 kPa. And to throw this in here, because sometimes people realize, well, I also measure pressure of my tires in a different unit, and that would be PSI, pounds per square inch, a force per area. That would actually be 14.7. The 13 there is page 13. So 1 atmospheric pressure is about 14.7 PSI. So if your tire is at 14.7 PSI, it's flat. Most of our cars operate somewhere between 30 and 36 PSI is a typical range. So you're talking about a little bit more than double atmospheric pressure. And literally, that little bit of air inside your tires is what holds your car off the ground. So air pressure can be a very, very strong force. Now, how do we measure air pressure? Well, we use a barometer. And what we really have is a column. Remember, I said a very specific diameter column of mercury. We use mercury because it's very dense and we don't need as large of a tube then. So it's easier to read with this kind of tube. Now, above the mercury, we're going to have a vacuum. So there can be no air above the mercury or this thing won't work. So what happens is the only thing that is causing that mercury to come down from the top of the tube would be gravity. So we have a column of mercury suspended over a pool of mercury, and gravity is pulling down on that. Well, how come it goes up if gravity is pulling down? Why doesn't it just pull it all the way down to the bottom? Well, you have to realize around the tube, air pressure is pushing down on the mercury, and it literally pushes mercury up the tube. And it doesn't push it all the way to the top because we have two competing forces here. We have the uh, gravity pulling down on the mercury, and we have the atmospheric pressure pushing up. And since gravity is a constant force, we can measure directly the atmospheric pressure by looking at the height of that mercury, a millimeter of mercury measurement. So when we're talking about atmospheric pressure, 1 atm was 760 millimeters. So what we're looking at here on the left is typical sea level atmospheric pressure. Now we go up on top of Mount Everest. We've got a significantly less amount of air above us and around us. So it's going to be at a much, much smaller pressure. So notice on top of Mount Everest, um, gravity wins and pulls the mercury down significantly lower until they become equal. And on top of Mount Everest, it's only around 253 millimeters of mercury on a typical pressure day. So it's significantly lower in pressure because you're very high up in the air. Now, how do we measure pressures of gases? Well, one way in doing that is with what's called a manometer. And there's actually closed-end and open-end manometer. So we're going to look at what's called a closed-end manometer. So it's a vacuum on the far side of that U-shaped tube. So we've got a U-shaped glass tube with mercury in it. And if the pressure on each side is zero, the only thing we have is gravity pulling equally down on both sides of the U-shaped tube, and the heights are going to be equal to each other. But when we put a gas over in the other container, or like in this case, we've got a liquid that evaporates to make a gas, we end up with gaseous ethanol, and it pushes on the one side of that column of mercury, and it's going to force it up into the air. Now remember, it's fighting against gravity, so it's not going to push it all the way to the top. And the height is actually directly related then to the pressure with which that gas is pushing on the mercury. And once again, we're looking at measuring a height of mercury here. So our U-shaped tube would have a very specific diameter. Now, one of the things that we should understand fundamentally about gases is gases have certain properties. And those properties are very predictable based upon the characteristics that we've been talking about. And one is that gases tend to have very, very low densities, significantly lower than solids and liquids do. And it makes sense if you think about it. Remember, the density equation is mass over volume. And while if we're talking about an equal amount of substance, the mass is going to be the same. Well, as a gas, it has a very, very large volume. It's going to spread out to can basically fill the container. So the same mass is going to be in a much larger volume. Well, in the density equation, if the number on bottom is getting big, that means the density is getting small. So really, this is because gases are far apart, low mass, high volume, directly related to kinetic molecular theory would explain why gases have low densities. Another thing that's true of gases is because they're far apart, there's space in between, and we can push gas molecules closer together under the right conditions, which means they're compressible. So gases are a compressible substance. Solids and liquids aren't. So this is a property that's very different for gases than solids and liquids. So if gases are far apart, they can be pushed closer together. Another thing that's true is if they're far apart and they keep rapidly moving in rapid straight line motion, if we move the walls out, the gases are going to expand. So gases will expand. So if gases are moving in constant straight line motion, they're going to expand to fill whatever container we put them in. Another property of gases is that they diffuse and effuse, two kind of related ideas. Diffusion is the tendency of molecules to move from an area of high concentration to an area of low concentration until uniformly mixed. And this is basically because if I open a container, I've got a very high concentration inside my container, but that gas isn't in high concentration elsewhere. So those gas particles are going to move out in rapid straight line motion to fill their new larger space. They're going to diffuse throughout that space. They're going to spread out. Like perfume being sprayed in the room. First, where it's sprayed, you can smell it, but eventually you can smell it further and further away. It's just not going to be quite as strong. So if we had a box with gases on each side and we opened the partition between the two, eventually the gases would diffuse within each other, evenly spread out. Now, a related idea, even sounds very similar, is effusion, the rate at which a gas escapes through a small hole. Now, this is not like putting a hole in a tire because that's a pressure different situation. It's under high pressure inside, and that literally is going to push a bunch of gas particles out. What we're talking about here is where we have a hole in the container, and as the gases are randomly moving around, when they hit the hole, they end up escaping. So the rate at which gases escape through that small hole is effusion. Now both diffusion and effusion depend upon the same thing, the speeds of the particles. The higher the speed of the particles, the faster they're going to diffuse, the faster they're going to effuse. So diffusion and effusion are really related to how rapid that straight line motion is for the substance. Now, that finishes really our look at gases. So that finishes our first set of notes from the chapter.